Welcome, everyone, to this deep dive.
hmm
If you're joining us today, you are likely navigating a pretty rapidly shifting landscape in cybersecurity.
Yeah, definitely.
I mean, whether you're a CISO, a developer, or just, someone trying to understand where all this technology is actually heading next,
hmm
today we are unpacking a really massive question based on a stack of fascinating new research.
Right. And it's a critical one.
Exactly.
Yeah.
Can artificial intelligence completely replace our traditional rule-based security tools?
Yeah.
And on the offensive side, how are these autonomous AI swarms currently being used to proactively hack into complex networks, like without any human supervision at all?
The contrast between those two applications is really where the most valuable insights live. We're looking at two very distinct studies today.
Two completely different worlds,
Yeah,
honest.
exactly. So the first one evaluates open source AI models as static defensive scanners, literally just having the AI read code to find vulnerabilities. And then the second study evaluates frontier AI models operating as autonomous multi-stage offensive hackers. Specifically, it's testing a system called YAGA in live environments to see if it can orchestrate a comprehensive cyber attack entirely on its own.
It is such a wild juxtaposition, honestly. But before we get into the actual mechanisms behind all this, I do want to say a huge thank you to today's sponsors, CISOmarketplace.com and Breach.company.
They're great.
They really are. They're the ones who make this deep dive possible. So if you're interested in the cutting edge of security infrastructure, you definitely want to check them out. So, okay, let's unpack this, starting with the defensive side.
Let's do it.
The first study pitted a pretty traditional security scanner called Bandit against three open source large language models. I think it was Gemma 3, Llama 3.1, and Qwen 2.5.
Yeah, those are the three.
And, I went into the source material assuming the AI would just absolutely crush the older software, but the data paints a very different picture.
Oh, it really does. The data provides a really harsh reality check. We're talking about static application security testing here, or ASAE.
Right, which is just scanning source code before it runs.
Exactly, before the software is ever run. And traditional tools like Bandit, they use deterministic rules. They parse the code into what's called an abstract syntax tree and look for known, rigid patterns.
Okay, makes sense.
So the study basically wanted to see if open source LLMs could do this better. And, well, the short answer is a definitive no. Developers must avoid relying solely on open source LLMs for code scanning right now. It's just not ready.
Yeah, the metric that really stood out to me was the recall value.
Oh, the recall was brutal.
Right. I mean, for those listening, recall measures the system's ability to find all the actual relevant vulnerabilities that exist in the code base. And the LLM's recall value has never exceeded 0.25.
Yeah, they were missing over 75% of the real threats.
Which is terrifying.
It is. And at the same time, their false positive rates were staggering. I mean, they were ranging from 49% to 90%.
90% false positives.
Yes. They were flagging perfectly benign code, like standard logging functions, as critical security flaws.
And the hallucinations were even more problematic, honestly. I was reading the logs provided in the research, and the LLMs were outputting completely fabricated file names. Like, how does an AI look at a static folder of documents and hallucinate a file that just isn't there?
Well, it really comes down to the fundamental architecture. You have to remember, LLMs are not parsers. They are highly advanced, probabilistic prediction engines.
Okay.
They don't load the code into a rigid memory structure the way a traditional compiler or a SAST tool does. They ingest the code as tokens and just predict what tokens should logically come next based on their training data.
So they're just guessing based on patterns.
Exactly. When analyzing complex repositories, their attention mechanisms drift. So they might associate a vulnerability pattern they've seen millions of times in training with the current code, and then probabilistically generate a line number, say, line 402.
Because it usually happens around line 400 in the training data.
Right. Because vulnerabilities often appear around that block in similar files, regardless of whether this specific file even has 400 lines.
That is wild. I mean, relying solely on that for automated code scanning feels like, I don't know, hiring a brilliant but incredibly sleep-deprived philosopher to proofread a massive phone book.
That's a great way to put it.
Right. They might spot a fascinating numerical pattern a normal person would miss, but primarily they're going to take an eternity to read it, and they will inevitably start hallucinating names and addresses that simply aren't on the page.
And the time disparity perfectly aligns with that analogy, too. Scans that took the traditional Bandit tool a few seconds required between 1 and 4 hours for the open source LLMs to complete.
Hours.
Yeah, Hours. And if a development team has to manually verify every single hallucinated file path and every false positive, I mean, the automated pipeline just grinds to a halt. The computational overhead is entirely prohibitive.
So if you're running a security team, do you just ignore LLMs for code defense entirely? Like, toss them out?
Well, no. What's fascinating here is that the real value lies in hybrid workflows. This is where the industry is seeing immediate return on investment. You do not use the LLM to scan the entire repository. You pair it with traditional SAST tools.
Oh, I see. So you let the traditional tool do the heavy, repetitive lifting first.
Precisely. You run Bandit, it flags the basic known issues in seconds. Then you use the LLM as an intelligent triage engine.
Okay, that makes a lot more sense.
Yeah, you feed the LLM the specific, localized outputs from the traditional scan and direct it to investigate the complex edge cases. You know, the weird logical implementation flaws that a rigid rule-based scanner just lacks the nuance to understand.
Right, because it's good at reasoning about those weird specific logic puzzles.
Exactly. And furthermore, the study highlights how these hybrid setups use LLMs to generate high-quality synthetic data, which is then used to better train the traditional rule-based tools, basically closing the loop.
I love that setup. The SARIS tool is the frontline guard, and the LLM is the specialized detective you call in to investigate the strange footprints.
Yep, that's exactly it.
But here's the massive contradiction that threw me while I was reading these sources. If an open source LLM gets completely lost just trying to read static lines of code, how in the world is AI successfully navigating live, chaotic network environments to conduct offensive attacks?
That sounds impossible, right?
It seems fundamentally harder. Yet the second study on the YAGA system shows it working incredibly well.
Well, the offensive landscape requires an entirely different operational paradigm. YGA is an autonomous penetration testing agent. It doesn't just scan, it conducts the complete life cycle.
Like everything from start to finish.
Everything. Reconnaissance, enumeration, exploitation, and post-exploitation. And it manages this complexity by completely abandoning the idea of a single monolithic AI brain trying to process everything at once.
Right. The sources describe YAGA operating as a swarm of specialized agents.
Yeah.
And I was really trying to wrap my head around how they coordinate without, a human central planner assigning tasks.
It's a really unique approach.
The best way I could visualize it is by looking at an ant colony.
Right.
Like when an ant finds a food source, there is no CEO ant giving a briefing to the colony.
No, of course not.
The first ant just leaves a chemical scent trail of pheromones on the ground. Other ants wander, smell the strongest trail, and follow it.
Yeah.
And then they reinforce that trail with their own scent. If the food runs out, the scent naturally fades, and the swarm organically redirects. Nobody is in charge. It's just decentralized coordination.
That is a perfect analogy. In computer science, we actually refer to that mechanism as stigmergic blackboard coordination. Yeah. Stigmergy is the mechanism of indirect coordination through the environment. So YAGA utilizes a shared blackboard rather than, a forest floor. And this blackboard is equipped with a vector search engine.
Let's pause there for the listener, because vector search is a term that's thrown around a lot right now. How does that actually differ from just hitting Secarel plus F on a database?
Good question. So traditional search looks for exact keyword matches. Vector search converts data into mathematical coordinates embeddings in a multidimensional space.
Okay.
It allows the system to find information based on conceptual similarity, not just text matching. So YAGA deploys these specialized agents. You might have a SQL injection agent, a privilege escalation agent, and maybe an SSRF agent.
Which is server-side request forgery, right?
Exactly, which is basically tricking a server into making an unauthorized request on your behalf. Now, these agents do not communicate with each other directly at all.
They just leave notes on the blackboard.
Exactly. They deposit their findings onto the blackboard, and the system assigns that finding a pheromone weight. This is a mathematical scalar value between 0 and 1, representing the utility and the temporal relevance of the discovery.
Wait, does it fade like the ant scent? Because a live network changes constantly. Like what works at 2:0 p.m. might be patched or blocked by an admin at 2:05 p.m.?
It absolutely fades. The system applies an exponential decay function to that scalar value. It's exponential rather than linear to ensure that stale information drops off rapidly.
Oh, that makes sense.
Yeah, if a path turns out to be a dead end or a server goes down, no other agents reinforce that finding. The pheromone weight decays to 0, and the swarm naturally abandons the path without requiring any centralized human intervention to, update a playbook.
I'm still trying to picture how a specific agent knows when to act, though. Like, if
Right.
the SSRF agent is just staring at this massive decaying math board, what tells it to wake up and actually do its job?
Well, they rely on trigger predicates. Each specialized agent constantly monitors the blackboard via that vector search we just discussed. An agent only activates when specific conditions emerge on the board.
Oh, so they're just waiting for their exact moment.
Right. For example, the privilege escalation agent remains entirely dormant until it sees a finding deposited that indicates a compromised system shell has been achieved, but that shell lacks root access.
And because of that indirect setup, the attack chain just builds itself organically.
The data from the study is remarkable on this front. 17% of YGA's successful multi-stage attack chains emerged entirely from this stigmergic interaction.
Wait, 17%? That weren't even programmed.
Exactly, they were not pre-programmed by the developers. An enumeration agent drops an open port finding. That triggers a classifier agent, which labels it as a vulnerable service. That deposit wakes up an exploit agent, which gains a foothold.
Wow.
The swarm combines vulnerabilities in completely novel sequences simply by reacting to the environment.
That is incredible. The effectiveness of this entire swarm, though, is heavily dependent on the actual AI models acting as the brains for these agents. So let's look at the benchmark testing where they pitted different models against each other. But first, just another quick shout out to our sponsors, CISOmarketplace.com and Breach.company. Seriously, make sure to check them out.
Yes, absolutely.
Okay, so the main showdown in the research was Anthropic's Claude Opus 4.8 versus OpenAI's GPT 5.5, specifically focusing on multi-stage attack scenarios.
Multi-stage is really the operative word there. Finding a single misconfigured bucket is trivial. We are looking at sequences that require chaining 5, 6, or 7 distinct vulnerabilities together to compromise a network.
Right.
And the study shows Claude Opus 4.8 consistently outperforming GPT 5.5 in these extended environments.
I noticed GPT 5.5 actually held its own on the shorter chains, though.
Oh, yeah. On 3-stage chains, GPT 5.5 is highly competitive. It actually outperforms Claude in highly specific localized tasks like complex JavaScript deobfuscation or parsing non-mainstream SQL dialects.
Okay, but then what happened?
Well, the architecture reveals its limits as the attack chain elongates. On sequences requiring 5 or more stages, GPT 5.5's success rate dropped significantly to 80%, while Claude Opus 4.8 maintained an 85% success rate.
Why the sudden drop-off for GPT? Does it just, like, run out of memory?
It's really an issue of maintaining adversarial context.
Adversarial context.
Yeah, as the sequence extends, the agent explores dozens of dead ends. It has to remember not just the technical details of the current server, but the overarching objective, the logic behind the steps it took 20 actions ago, and why a certain path was previously abandoned.
Oh, okay.
GPT 5.5 struggles to hold that strategic thread over long horizons, whereas Opus 4.8 retains a much tighter grip on the contextual memory required for sustained exploitation.
Here's where it gets really interesting, though. The data showed a weird anomaly regarding the older Anthropic models. The older Claude Opus 4.6 actually beat the newer Opus 4.7 model in these tests.
Yeah, that was a huge surprise.
Usually, a higher version number means better performance across the board. What is the mechanism that allows the older tech to win here?
The variance basically comes down to a concept called uncertainty calibration, and it is specifically highlighted during gray box testing.
Remind us what gray box testing is.
Gray box testing is a scenario where the AI is given partial information. So perhaps it starts with a low-privilege user account or incomplete API documentation. It has some context, but not the full map.
Okay, so how does the older 4.6 model handle that partial map better?
Well, Opus 4.6 demonstrated a highly conservative uncertainty calibration. When it encountered a blocked path, its internal confidence scores dropped appropriately. It recognized its own lack of knowledge.
That sounds like a good thing.
It is.
Hmm.
Behaviorally, this caused the model to pivot laterally. It actually attempted 23% more unique exploratory actions than 4.7. It looked for alternative horizontal paths across the network. Opus 4.7, on the other hand, possessed a severe high-confidence bias.
It was too sure of its initial assessment.
Exactly. From a mathematical standpoint, its probability distribution favored immediate exploitation over exploration. So, given partial information, 4.7 attempted to force direct vertical privilege escalation.
And when that didn't work?
When that failed, instead of recalibrating its uncertainty and looking elsewhere, its confidence remained artificially high. This trapped the model in endless retry loops, basically just attempting the same failed exploit with minor variations over and over.
That makes perfect sense. The newer model gets stuck trying to bash down a locked door, while the older model recalibrates, walks around the building, and looks for an open window.
Exactly.
This brings up a really foundational question for me regarding how these systems are trained. In a massive enterprise network, an AI might have to take hundreds of actions, scanning ports, parsing logs, mapping empty servers before it ever receives a meaningful reward, like a brute shell.
Right.
How does the system stay motivated to keep searching during those long, empty stretches?
You're hitting on the sparse reward problem, which is honestly one of the hardest challenges in reinforcement learning. YAGA solves this by utilizing a curiosity bonus mechanism.
Curiosity, like human curiosity.
Sort of, mathematically speaking. It's implemented through an architecture combining proximal policy optimization, or PPO, with random network distillation, which we'll call RND.
The sources dive really deep into the math there. Can you lay out how R&D actually generates curiosity in a machine?
Sure. So R&D utilizes two entirely separate neural networks running in parallel. The first is a fixed target network. Its weights are randomized at initialization and they never change.
Okay.
When the AI agent observes a new state in the network environment, say a specific server configuration, this fixed network processes that state and outputs a mathematical vector.
It basically generates a totally random but consistent barcode for whatever room the AI just walked into.
That is a perfect visualization, a consistent barcode. Now, the second network is a trainable predictor network. Its sole objective is to look at that same server configuration and attempt to guess the exact barcode the fixed network is going to generate.
Wait, if the fixed network's barcode is completely random, how does the predictor ever guess correctly?
Through repetition and training. If the AI agent has seen this specific type of Apache server configuration 100 times, the predictor network has trained on it extensively. Its guess will be highly accurate, meaning the prediction error is very low.
Oh, I see.
But if the agent stumbles into a truly novel state, perhaps a legacy, custom-built internal database it has never encountered before, the predictor network has no training data for it. Its guess will be wildly off, resulting in a massively high prediction error.
And the system uses that error as the reward.
You got it. The architecture translates that high prediction error directly into an intrinsic curiosity bonus. It alters the reward function, so the AI receives a dopamine hit, mathematically speaking, simply for discovering novel states, even if those states haven't yielded a tangible exploit yet.
It's exactly like the fog of war mechanic in a strategy video game.
Oh, totally.
Right. When you load into the game, the map is black. You don't know where the enemy base is. But early on, the game inherently rewards you for sending a scout out to clear the dark areas. You get value from the exploration itself.
The challenge, then, is balancing that exploration with actual exploitation. The mathematical coefficient governing this curiosity bonus is annealed, meaning it is systematically reduced over the duration of the engagement.
So it fades over time.
Yes. In the early phases, the agent is driven almost entirely by exploration, clearing that fog of war. But as the engagement matures, the system dials down the curiosity multiplier. It forces the agent to shift its focus strictly toward exploitation, demanding extrinsic rewards like actual privilege escalation and data exfiltration.
But how does it know when it's truly finished? Like, if the curiosity dials down, does it just keep running the same exploits until a human unplugs it?
No, YAGA employs formal stopping criteria based on information gain and entropy reduction. This is known as the epistemic criterion.
Epistemic. Yeah.
The system continuously evaluates a rolling window of its recent actions to measure the reduction in entropy. In this context, entropy represents the AI's uncertainty regarding the network environment.
So when it first drops into the network, entropy is at its absolute peak.
Right. And every subsequent action reduces that uncertainty. But eventually, the agent maps the perimeter. It begins encountering the same standard configurations and the same patched software. The rate of entropy reduction begins to plateau.
It's not learning anything new.
Exactly. When that reduction in uncertainty falls below a specific mathematical threshold for a sustained duration, the system calculates that it is no longer gaining meaningful new information. The exploration has mathematically reached saturation, and the agent automatically terminates the engagement.
It literally hits a mathematical asymptote of new information and stops.
Yeah.
So what does this all mean? We start by asking if AI can replace our traditional security tools. And the data really tells a very bifurcated story.
It does.
On defense, open source LLMs are nowhere near ready to operate independently. They hallucinate, they're incredibly slow, and they require hybrid workflows where traditional rule-based scanners do the heavy lifting. But on offense, frontier models are already highly capable of coordinating autonomous multi-stage attacks.
Without a doubt.
They don't rely on linear human playbooks. They operate as decentralized swarms, utilizing stigmergic blackboards,
Yeah.
driven by mathematically engineered curiosity.
And, you know, the efficacy of that offensive swarm brings up a really critical implication that extends beyond just the technology itself. If we have autonomous AI swarms dynamically interacting with live networks, learning and combining exploits in novel, unpredictable ways, we really have to consider the liability of emergent behavior.
Liability, what do you mean?
Well, think about it. If a YAGA-style offensive swarm is deployed by a security firm for a routine penetration test, and through its decentralized stigmergic coordination, it organically develops a zero-day exploit it was never programmed to find.
Oh, wow.
And in the process of testing it, inadvertently crashes a hospital's critical infrastructure. Who holds the liability?
Is it the developer?
Is it the developer who coded the agent? The creator of the foundational LLM, the CISO who authorized the swarm? We are deploying autonomous agents into critical environments before our legal and operational frameworks have any mechanism to handle emergent, unprogrammed destruction.
A swarm that is mathematically rewarded for finding the unknown is eventually going to find something we really wish it hadn't.
Exactly.
It's a sobering reality to consider as this technology scales. Well, thank you all for joining us on this deep dive into the AI security frontier. And one final thank you to our sponsors, CISOmarketplace.com and Breach.company for making this possible. Keep questioning the consensus, and we will see you next time.